when computer scientists start telling neuroscientists how the brain works, we need to be cautious. If you had a whole brain, let's just say that someone gave you a whole brain on neuromorphic chips, and it had every connection and all the dynamics you needed to replicate a brain, mouse brain, say.
Yeah. Then
we're going to be where we are now in systems neuroscience, and how do we interpret what's going on in that?
Right.
This is Brain Inspired.
Welcome, guys and gals. I'm Paul Middlebrooks. Today, my guest is Brad Aimone, a neuroscientist turned AI researcher / neuromorphics and computing researcher at Sandia National Laboratories in Albuquerque, New Mexico. Can you spell Albuquerque? So this was fun because I haven't had anyone on the show talking about neuromorphics since way back when, what episode was that with Julie Grolier? Episode 19. Wow, long time ago. I came across Brad because I learned about his method of transforming a normal deep learning network that uses rate-based signals into a spiking neural network that uses spikes or event-based signals like brains do to allow the transformed network to run on neuromorphic hardware, a method that they call the whetstone method. But as I dug deeper, I discovered all of the other interesting stuff that he does, and we ended up talking for a long time because the man was generous with his time. And for that, I am grateful. But because we talked for so long, I split our conversation into 2 episodes. So in this first part of our conversation, we talk about what I just described. We also talk about Neurogenesis deep learning, which is a way to add artificial units to deep learning networks as the networks get trained. So this is inspired by how new neurons are generated in our hippocampus. And we also talk about the neuromorphics workshop that Brad co-created and helps run, the Neuro Inspired Computing Elements workshop, or NICE workshop. And you can find links to all of the stuff that we talk about, as usual, in the show notes at braininspired.co/podcast/41. For example, you can find a link to the NICE workshop where they host videos of all the talks and panel discussions from the workshops of years past. All right, here's part 1 with Brad Aimone. So I'm doing some research about my next guest, and I'm thinking, this is going to be great. I haven't talked to neuromorphics on the show since I had Julie Grolier on the show a long time ago. And this is someone from the more of a computational, computer science-y background. And lo and behold, I have another damned neuroscientist on the show. So, Brad, welcome to the show.
Thank you.
So you do have a neuroscience background. You did a PhD in Fred Gage's lab studying adult neurogenesis in hippocampus, among other things. But now you're at Sandia National Laboratories, where in Albuquerque, New Mexico, where you're working with neuromorphics and computing in general and developing new techniques in AI. So just to start off, how did you come from the neuroscience world to this current Sandia National Laboratories world?
Yeah, so, like most people's kind of career trajectories, mine took me on some unexpected paths. When I was leaving the Salk Institute, where I was a computational neuroscientist working among molecular biologists and neuroscientists, I really wanted to identify a path by which the work I was doing in computational neuroscience could have some more tangible real-world outputs.
Yeah.
And this is always a struggle, especially, I think, for systems and computational neuroscience, where the kind of classic application for neuroscience is health. And, like most people, I had very interesting ideas, I think, at the time. I thought they were interesting, of how my research could play into, mental health disorders and psychiatric disorders and so forth. But the more you push it, it's a really long path to go from computational neuroscience into anything that might have clinical relevance. Most clinical research is focused on drug discovery, for instance. So I got an opportunity to talk to people at Sandia, which as a national laboratory doesn't do a lot of neuroscience. It certainly doesn't do anything close to the experimental neuroscience that you would have in San Diego or any of the other big hubs of neuroscience. So I wasn't sure what I was going to get into when I came out and interviewed. But the upshot is that national labs, while their mission's not health, it's not NIH funded, they focus a lot on physical sciences, computer science, and fields like that. And so there's a lot of interest among this community, and there has been for 10 years or so, in future models of computing. So neural brain-inspired computing fits right into that. So they wanted to bring people in with neuroscience backgrounds in order to start thinking about what the future generations of computers would look like. I was like, you have big computers, and I like to do big simulations, so, that sounds fun. Let me go play with those big computers. So it was I saw it as a mutually beneficial thing. I'll tell them a bit about the brain. I get to play with their big computers, and we'll see what happens. And, so I did that. I came to Sandia for really with the goal of doing what I was doing before, which was modeling hippocampus circuits, looking at things like adult neurogenesis at larger and larger scales. So pushing the envelope of how big of a simulation one could do. Of course, there are issues with that. The field as a whole has been trying this in a number of areas, and I ran into similar issues. Biggest one being that you can always build a bigger and bigger simulation, but ultimately you're constraining your models based on individual recordings of isolated neurons, and you're trying to kind of go from electrophysiology data to something that exists at a very large scale. And how much you can glean from models constructed like that is a challenge. I don't, I've been struggling with this my whole career, and once I got kind of isolated from the experimental community when I came here, it almost opened my eyes a little bit, saying, in order to convince an experimentalist to start modeling, to do experiments to study what my models produce, that would be a really tall order for them. And so we kind of had a nice, I'd say, almost soul-searching moment of being a neuroscientist doing really, really large-scale simulations. Yeah. So from that point, I kind of started to embrace the sort of computing applications of neuroscience more than just simply using computing as a tool.
They've turned you. So this is like, how long have you been at Sandia now?
About 8 years. I think I came here late 2011.
So, I mean, this is an interesting transformation. Like you said, everyone's career takes a winding path, but so you've been slowly, from my own research, it looks like you've been slowly becoming more and more enamored with the computing aspect of all of this. But you're definitely influenced by your knowledge of brains and hence the neural inspired computing aspect of all this. So when you approach a problem, do you view things now through the lens of the potential for its computing ability, or do you view it through the lens of the potential of its relation to brain, what we know about brains, for instance?
I think it depends. It depends on what it is that we're trying to do. In the case of something like deep learning, there are times where you want to make it more brain-like. You want to add some capabilities, some functionality that, it'd be great if our algorithms could do what our brains are able to do. And in those cases, I think, looking to what the brain does seems the natural and almost easiest path by which we can get that capability into these algorithms. On the other hand, there are going to be cases where, we've used the brain to inspire the hardware architectures that the neuromorphic community is developing. And now we can just think about it from a computer science point of view. It's like, given this computing fabric, what problems can we solve that are new? And that can take you in a direction that's completely unrelated to how the brain functions, or at least we can set aside that constraint, move towards, asking what is a computer made of neurons effectively able to solve more efficiently than a computer made of kind of conventional logic gates. So we do both, and I've enjoyed kind of switching back and forth between those different mindsets. And admittedly, I probably confuse people because sometimes I'll be like, look, the brain does this and this and this, and you need to do it that way. And other times I just jump at something and say, let's ignore the brain, let's do it a different way. And I think there's reason to do both at different times.
Well, you're like the only neuroscientist in the room ever, right?
That's not true, actually. We have another neuroscientist here, Francis Chance, who was a professor at UC Irvine for a while and came out of Larry Abbott's group a number of years ago.
Mm-hmm.
So we have two computational neuroscientists around.
I like what you said earlier about sort of the struggle with the frustration with the clinical relevance not being in a shorter run, like the clinical relevance being in the longer run from a computational neuroscience perspective. When I was in graduate school, the mantra was, I think it was from benchtop to bedside. And this is like the idea that your research is directly applicable in the next step to treating people. And from a computational neuroscience perspective, that is not the way it works. So we all just kind of rolled our eyes,
Yeah.
All right. So let's jump in here. So I have so much to ask you about today. So we'll see how far we get. But
Okay.
Let's start with some of your recent work here, and then hopefully broaden the conversation to neuromorphics in general and neuroscience and AI. So you developed what you have called neurogenesis deep learning. And maybe before we discuss it, just as background, maybe you can summarize your work a little bit on neurogenesis and memory in the hippocampus from your PhD work.
Yeah, so I think my true neuroscience love are new neurons in the hippocampus.
Yeah.
So, I was in Rusty Gage's lab as a grad student and for a short postdoc. And that lab, before I got there, had been one of a handful of labs around the world that had identified that indeed you have new neurons born into adult brains. And this is still a mildly controversial topic, but at the time, it was very controversial. Historically, the textbooks I read as a kid, biology classes in high school, there are no new neurons in adults. I mean, that's fairly accepted dogma at the time. Well, it turns out that there are. And in particular, the dentate gyrus area of the hippocampus receives a fairly robust level of neurogenesis throughout life. It's robust in that it always happens, but it's not a ton of neurons. It's just kind of a continuous stream of new neurons coming in.
Well, it's not so much controversial that there are new neurons being developed in the brain in hippocampus, right? Isn't it more controversial that it's in other areas as well, that it's ubiquitous? What's the controversy?
So there has been controversy about both. Okay. So while I was in grad school, the big controversy at the time was whether cortex received new neurons. There were some reports out of Elizabeth Gould's lab, I believe it was, that had inhibitory neurons being born in different cortical regions. And those were, Pascal Rakish in particular was very adamant that they were not there. I think it's still an open question about whether some of these interneuron populations in different parts of the brain indeed have adult-born levels. And in some ways, I think that's a limitation of the tracking tracer tools that we have. But lately, there's been a bit of a renewed controversy around whether humans have adult neurogenesis. Most people would say they do. Studies going back to the late 90s from Rusty and Peter Erickson said this. There have been more recent works by Jonas Friesen and others that are looking at kind of radiation tracking from above ground nuclear tests in the 60s. You can use that to track whether there are new neurons in different parts of the brain.
Right.
And you see that this happens in dentate gyrus in humans, in postmortem tissue using these radio labeling studies. So it's pretty convincing evidence. But there are a few groups that continue to publish fairly high-profile studies that say it doesn't happen. So, I'm not a molecular neurobiologist. I am not an expert on the tracer study, limitations of different tracers and so forth. But from what I can tell, it does seem like you have a robust level of new neurons in healthy adults. I think that if you have certain disease conditions, and certainly with aging, there is a reduction of these new neurons. So, depending on what population of people you're testing, you may not see very many of them, if any at all. But I think that it's probably safe to say that most people listening to this are having new neurons integrating into their hippocampus today.
Thank God. Our hopes and our dreams hinge on this very fact, my friend. So
yeah, help us all remember the conversation.
That's right. Right. Okay. Well, so anyway, so what work did you do?
So when I started in Rusty's lab, the challenge really was, what are these new cells good for? I had a colleague that kind of related it as, why would you rewire a 747 in the middle of a flight? It's kind of a conceptually challenging thing to do. I'm going to plug new neurons into a functioning, awake, active brain. And so there had to be some computational reason for this. So I approached it by basically building neural simulations, looking at relatively biologically constrained models of the dentate gyrus, using thousands of individually modeled neurons, using different interneuron populations, looking at grid cell inputs, various other sorts of inputs. So my thesis was really focused on what adding these new cells into the circuit would do from a information theoretic point of view. The kind of initial thought at the time, and I think it still kind of persists, is that the dentate gyrus is responsible for what's called pattern separation. The idea that when you form a new memory, you might have two concepts that are effectively pretty close to each other. You can think of a green apple and a red apple. They're both apples, but one might be more tart than the other. And so we would like to have some way of actually encoding those differently, make sure that when you form your memory of whether you had an apple, you encode it as a green apple or a red apple. You're not confusing those two things. And so the dentate gyrus has long been associated with this pattern separation function. And what was interesting about the work that my models kind of produced and those results was that these new neurons coming online changed how the dentate gyrus did this pattern separation, at least in simulation. And there were a couple of key findings. One that I still like, although I've never found a good use for it, is that the cells are active over a certain finite period of time. So in a sense, they kind of allow you to form associations of things that are contemporaneous with one another. So the idea that if I hear a song that was a hit in 1986, I'm going to think about a vacation I did with my family in 1986, that the song was at the same time as that vacation, even though I may not have heard that song during that vacation. I'm going to associate those two memories in time. And it's because the new neurons coming online overlapped with one another.
Right.
So that's one theory, the sort of theories that these models produced. The other one that I think was more useful is that we really looked at how neurons could encode information that was novel. The challenge, if you think about that, I mean, it sounds almost trivial, but if you have a neuron that has thousands of inputs that generally you don't want to fire unless it's responding to something that it's been trained to respond to, getting that cell to fire to something novel is actually really hard because the brain is more or less wired not to be noisy.
Right.
I don't mean noisy in the sense that people see kind of population activity that looks noisy, but rather you don't want neurons firing to completely random arbitrary things. You want neurons firing in a reliable, predictive manner. And so how do you get a neuron that's fully formed, that has thousands of inputs, that is generally inhibited to fire to something new? Turns out that it's actually very hard. You can do some very simple models that say that the sort of sensitive range where you can actually tune a neuron to fire to something novel but not fire too much is very, very narrow. Turns out these young neurons actually are very good at responding to novel things. They're, in a sense, like college kids without a major. They try out all sorts of new stuff. And then eventually they gain synapses and they refine themselves to whatever it is they learn to fire to. But during that short period of time, they're open to novel responses and they're able to learn to fire to novel things. And that finding actually has become a more directly tangible tool for use in kind of further computational development.
So this is a good segue then to fast forward a year or two. I don't know how long this was simmering, but so then you decide, deep learning networks. Maybe they could have some new neurons too, huh? Is that how it worked?
Yeah, it's kind of the natural thing to do if you have my background and you move into computing.
Yeah.
So I'll say that when I first started doing this neurogenesis stuff, there were people doing neural networks in the early 2000s, 2002, 2003, adding new neurons into trained neural networks and showing that they could avoid something called catastrophic interference.
Yeah.
So neural networks have this problem, and this is the case of probably any of the neural networks that people are familiar with today, deep learning nets and so forth, that once they're trained up on something, if you keep adding new information into those networks, you can either tell them, okay, I don't want you to learn anymore. So you basically lower the learning rates so that they're very hard to train past a certain amount. Or you just keep adding new information to these things, and eventually all the things they've learned in the past just collapses. And you get this interference effect where they've added too much information onto a network that just doesn't have enough capacity to handle it. So people showed years ago, 2 decades ago, that new neurons could ameliorate this effect of catastrophic interference. But they never did it, they did it for kind of early 2000s neural net purposes, which of course is completely different than the deep learning generation we live in today.
Connectionist models or something, right?
Yeah, absolutely. These were, they're good models and they influenced me. But as far as I know, the people who did this stuff never went into the deep learning field. So we were looking at deep learning kind of as an emerging thing a number of years ago. It's probably been 4 or 5 years ago now. And the idea that, these deep learning nets, you train them on a lot of data, and you might want to apply them to a new world, right? Something that's slightly different than the world they were trained up in. And that's exactly the case that we think that adult neurogenesis in our brains is useful for. So if I want to do with this deep learning model, what a human would do, and that is expose it to novel information, novel contexts, how do I adapt that model? So we decided to basically just do the simplest thing possible. That's stick new neurons into the deep learning nets. And of course, it adds complications. These are deep networks. Where do you stick those where do you stick those new neurons into?
Yeah.
For instance, it's not, there are a lot of things you can do there, but then that's kind of the direction of research we took.
Maybe we can talk just a little bit about so you run into this multiple issues, like you said, one of which is just how to train the network once you add the new neurons. And my understanding is that the neurogenesis training works based on essentially how wrong the network is, how big the error is once you put a new, well, maybe you can just tell us how wrong or how big the error is. So how does it work and what did you find?
Yeah, so the challenge I think that you're alluding to is, if I have the ability to add a new neuron to my network, when do I need to add that new neuron, right? When should a network just say, okay, here's a picture of something, classify it as a dog or a cat or whatever, or recognize that that's a new class, that's a dolphin and it wasn't part of my training set and I need to adapt my network to handle it. And this is really the core problem of these adaptive models. We want our models to behave on data that's not part of the training data. That's the reason they're useful. But if something's novel, is it just a different point that would effectively be part of the training data, but it just isn't? Or is it something that's completely different that my model needs to change to? So what we did is we looked back on some of the early deep learning literature, which were very much based on things like autoencoders. And the idea of an autoencoder is my network will train a network to reconstruct the input images.
Mm-hmm.
And these are pretty useful models, at least for an academic study like we did, where it gives us a very clear metric of whether the model is able to represent an input piece of data or if it just is failing at representing that data altogether.
A really high level, you input an image into this autoencoder, and then basically it kind of compresses relevant features then to attempt to reproduce that same image. Do I have that right?
Yes, and that's the basic idea of an autoencoder. You go from one layer that might have 1,000 neurons, and you'll go through a few layers, you end up at 100 neurons, and then you go back through that network until you get to the outputs, which are the same as the input layer.
Yeah.
And you get back to that 1,000.
Okay.
And so it's a measure of lossiness, in a sense, is how much you can compress the data and decompress the data and get back what you started with.
Gotcha. Okay.
So, for neuroscientists who aren't familiar with deep learning and these networks, lots of people are familiar with PCA. And PCA is, in effect, can be thought of as an autoencoder where your neurons are just linear units.
Right.
And the idea of PCA is you go from a high dimensional space into some lower dimensional representation. And from that, you can go back into that higher dimensional space. And that sort of compression and decompression. And that can tell you how complex the sort of lower dimensional structure of your data is.
Okay.
So these autoencoders you could think of it as a deep PCA that has some nonlinear units in there. But what's nice about this is that you can actually do this sort of step through as far deep into a network as you want to go. So if I imagine I have a 5-layer autoencoder, I can actually go from layer 1, which is my input layer, to layer 2, and I can go back to layer 1, and that tells me how effective layer 2 is at representing the information in layer 1. And I can go 1, 2, 3, 3, 2, 1, 1, 2, 3, 4, 4, 3, 2, 1, and just keep going deeper and deeper in the network. And what we found was that these networks that were constructed to represent handwritten digits, because everyone does handwritten digits as a first step in deep learning, you see that, okay, the first couple layers tend to be, they're looking at effectively looking at things like edges and very low level structure. So they just kind of do their thing. So the idea would be that you go in and out and you measure how well that layer can represent. Well, the first layer usually represents things pretty well, even if it's novel, because it's looking for fairly simple things.
Right.
But as you went deeper into the network, you start observing that I add a new handwritten digit. Turns out my network just can't represent that anymore, 3 layers in. And so if it can't represent it 3 layers in, it certainly is not going to be able to represent it 5 layers in.
Mm-hmm.
And that tells us where you want to kind of focus adaptation might be 3 layers in. And so we would then maybe add a new neuron or change the learning plasticity rates or whatever at that 3rd layer, have it learn the new information. And then we've maybe fixed the 3rd layer. Now we move on to the 4th layer and 5th layer and so forth. So it's this iterative.
Okay, yeah, that's what I was going to say is iterative, yeah.
It becomes an iterative process, but you end up identifying through this sort of autoencoder structure where the network is beginning to fail.
So we don't need to spend too much time about it on this, but I'm just curious. So did it become an automated, is there an algorithm to determine, I guess there was an algorithm to determine, okay, add the unit now in this layer if it triggers this big of an error.
Yep. So we had basically an algorithm that was pretty heuristic based of saying, if your error passes a certain amount, add a new neuron here and then retrain. And then we also had a component which did a version of replay similar to what we would see in the hippocampus, where you have kind of reactivation of neurons. And we had this replay that was then used to kind of help train that new neuron and make sure it plays nice with the existing neurons around it.
I must be making so many new neurons because I make so many really large errors. Hopefully that's the case. I don't know how that works.
Yeah, no, I think, I would suspect that the brain actually does this sort of thing, right? I mean, we add new neurons and we plug them in, and then if it doesn't work, they kill them off and they put new ones in. So
yeah. Well,
it's not unreasonable to think that we could come up with ideas going back into the brain from this.
It's actually a recurring sort of worry of mine with this whole endeavor of like building neuroscience concepts into AI. Obviously I'm all for using what we know about brains, to build better machines. But like, for example, neurogenesis, right? You've already said like there's controversy over whether it even happens. And we don't know exactly how it happens. And this sort of our level of understanding of what's going on in brains is pretty ubiquitous across almost any subject area when you come to the state of art in neuroscience. And I wonder if we run the risk of sort of incorrectly implementing these concepts that we think we understand from neuroscience, trying to implement them into machines, into AI, and if that's just going to run us into trouble along the way, right? Does that make sense?
It makes sense, and I think it's a fair worry. I would say that there's reason, I think, to be worried about it, and there's a reason that we probably shouldn't be worried about it. I'll start with the reason not to be worried about it. I have found that the computing field, the machine learning field, the general computer science field as a whole, they don't care about how the brain works.
Right.
I mean, They care like anybody on the street does. They'd like to know, but ultimately what they want to do is they want to solve problems.
Mm-hmm.
And so if someone comes with a neuroscience interpretation, and it turns out that from a neuroscience point of view, just isn't what happens. It's just not what the brain actually does. But it changes how machine learning is able to solve a certain task that no one had been able to solve before. Then I think neuroscience actually has won, because there's been an improvement in the world. We've been able to improve some capability of computing in a way that would not have happened without neuroscience being there in the first place. And I would almost guarantee you we see some stuff like that today. Right now the machine learning field is running with reinforcement learning, and they're running with reinforcement learning on a interpretation, I think, of literature from the 80s and 90s that probably would make most neuroscientists a little bit uncomfortable. But it's changing the way AI is functioning, and it's doing amazing things. So I think we should embrace that. And as a neuroscientist, I don't critique people for having the implementations in these models not be perfect with how the brain does it. So that's the reason I don't worry about it.
Yeah.
The reason that probably is worth worrying about is that while AI and computer science and machine learning are very much focused on what works, the neuroscience field, if we ultimately do want to get back and cure diseases and so forth, which I think really is the goal of the field in a lot of ways, it doesn't do any good to go back in and say, hey, the brain is a giant deep learning model, because deep learning is really effective at doing these tasks that historically we've relied on humans to do. Because that's not going to help us cure Alzheimer's. Like, I find it hard to imagine that a deep learning interpretation of the brain is going to help us cure a disease. So I feel like as long as we're accepting of the fact that the AI field and computer science field can use a abstracted coarse approximation of neuroscience and do great things, we want to help that. It's perfect. But coming back the other way, we need to acknowledge the fact that there was this sort of compression of knowledge going in that direction to begin with. And I think that when computer scientists start telling neuroscientists how the brain works, we need to be cautious.
Yeah, I agree with everything that you just said. To me, I was talking with my friend just the other day, and I pulled the, hey, I've got a PhD in neuroscience card. And I said, and everything I read in the popular media, or even in like popular science media about quote unquote, how the brain works is just wrong. And so what's really disappointing, of course, we were talking about this in the context of politics, but what's really disappointing is then what I know is that anything I read from any other field with like these claims is that I know that information is almost certainly wrong.
Yeah.
But we still take it as all right. So as all correct. So the headline will be like for this neurogenesis deep learning is in Time magazine or whatever. I don't know that shows my age that I'm referencing Time magazine, but the headline will be machines use what we know from neuroscience to improve learning in such and such field. But the key nugget there is we don't actually know that in neuroscience. So it's an interesting cycle, right? Of having said that, I do agree with everything that you just said. But that's the neuroscientist's frustration is no, we don't understand, in fact.
Yeah, but, so I agree. And I think the issue is based on what we do know, or maybe what we think we know, but know that we don't know perfectly.
Yeah, there you go. There's some metacognition.
Yeah. What can we do with it? Is there anything useful to do with this information?
Right.
And we want to avoid being in this sort of paralysis of perfection. And the brain's really complicated. And if we insist on not moving beyond the hallowed halls of a neuroscience institution into the real world until the thing is perfect, then the world's going to bypass the community, right?
Yeah.
And I actually think in the case of computing, we see this where the neuromorphic community and the machine learning community both, they just started doing stuff without neuroscientists really telling them what they could do and why they should do it and so forth, because the neuroscientists were busy fighting with each other, and I was part of that about, what a place cell is, for instance. And that's fine. I think as a community, we need to always be trying to improve on what we understand, what we do. But when we have an opportunity to export knowledge with all the caveats that may need to go with it, but if we have the ability to export some sort of insight into how computation works or into how the brain might be treatable for a disease or whatever, we need to embrace that opportunity and not become paralyzed by self-imposed requirements that we have it entirely right.
I think this is a really good example, this neurogenesis deep learning, of a real advantage, for all of us, that someone like you went from academia into this more computing space. And this is a great example of building in something related to neuroscience and trying it out to solve problems. So, along the lines of what you were just saying, this just serves as one of many examples, I think. But it's cool work. So nice job.
Thank you.
Sammy, Jonathan, Kihong, your souls will be going directly to heaven when you perish, if you don't upload your souls to the internet, of course. Not that you'll ever perish. Anyway, thank you for supporting the show. This show depends on and runs on your support. I don't do ads to try to sell you mattresses and so on, although I do love my mattress. Maybe I'm laying on my mattress right now. Anyway, you can support the show for as little as $2. Go to braininspired.co and click on the red Patreon button there. So let's transition just a little bit toward the neuromorphics. And this is actually the original thing that was the impetus for me to contact you and research what you're doing. And that's the whetstone method. So this is another recent project that you've worked on. And it's basically a way to take a normal deep learning network and transform it into a spiking neural network so that it can be used on neuromorphic hardware. And we'll unpack that in just a second. Well, I don't think I've had any guests that I've talked with on the show about spiking neural networks yet. So this is exciting. So for clarity, what's the difference between traditional deep learning nets and spiking neural networks?
Yeah, so deep learning nets and probably 99.99% of artificial neural nets that have ever been made don't have the sort of intrinsic dynamics, the activations that we see in neurons in the brain.
Yeah.
So neuroscience audience, everyone knows that neurons have action potentials They're fairly complicated biochemical mechanisms by which, you get Hodgkin-Huxley dynamics and so forth.
Yeah.
But even if you simplify that and you have like an integrating fire neuron, it's just, okay, my inputs cross a threshold, I get a spike, and that spike propagates down an axon to other neurons. That's what neuroscientists learn from day one, basically. On the other hand, artificial neural networks really are nothing like that. They have neurons that are, nodes or neurons, whatever you want to call them. They're connected to other neurons, but they aren't sending spikes in between them. They're basically sending some sort of continuous value. And maybe it's a sigmoid activation function. The trendy thing these days is a rectified linear unit, where, above a threshold, I send some value, and that value can be from 0 to infinity based on how far over the threshold I am.
Yeah.
And so whether it's a sigmoid or a rectified linear unit, or, pick whatever function you want to use, it doesn't really matter. But the deep learning field has made a lot of progress in this sort of continuous valued view of how neural networks can work. And that's great, and they've been very successful.
So let me just interrupt just to be like super, super ridiculous. But one way to, I guess, not visualize, but auditorialize this would be like in a deep learning net, the units communicate with something like doo, whereas in a spiking neural network, they communicate with pop, 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 pop. Would that suffice, you think?
That's right, and I'm glad you did that, not me.
Yeah, well.
Yeah, no, I think that's exactly what happens. And from an information theoretic point of view, the continuous valued neurons are better. There's more information encoded in those neurons.
I see.
And we see that even in the case of biology. C. elegans, retinal, pre-ganglion cells in the retina, like bipolar cells and cones and rods, they're all more or less continuous valued outputs.
Right.
So the issue is not that spikes are better per se, but what ends up happening is that our brains, I think from a theoretical point of view, why would our brains use spikes when continuous valued neurons are more information rich, is that the spikes actually confer very strong signal to noise benefits and very strong energy benefits. And using things like temporal coding of when a spike happens, you can recover a lot of that missing information that was in the continuous value. So neuromorphic hardware, there are several ways of doing neuromorphic hardware, but one of the ways that's been really successful in the last 10 years, and IBM has been leading this with their True North chip, Intel has their Loihi chip, Human Brain Project has a number of chips, Spinnaker and BrainScale's chips, and they all use spiking as a mode of communication. And the reason they use the spikes is that you're sending an event. You're sending a 1 or a 0, but usually only send the ones. If it's a 0, you don't send anything.
Right.
And that's incredibly energy efficient because you're just not moving information around. You're just sending a 1 every once in a while. It's just, like you say, a pop. And that's enough.
Is the energy efficiency, is that the main impetus behind these big corporations developing these neuromorphics, or is it multifold?
I'd say energy efficiency is the most immediate reason for doing it.
Okay.
There is a hope that by building hardware in the shape of how the brain functions, or kind of is structured, let's say, novel capabilities and algorithms could come in and change how we use computers. That's, I say, a medium to long-term goal.
These are like their research and development parts of their company that have this longer-term investment with a longer-term return on that investment in their vision. Huh?
Yes.
Yeah.
Yeah, most of it is not trying to make money today. They're trying to make money, 10 years from now.
Right.
And there are some deeper reasons why energy is increasingly a concern to these companies.
I see. Yeah, sorry for the interruption. I'm curious.
Yeah, and I can talk about that, the energy, the reason of why we want to push energy in a minute if you want.
So. Yeah, well, let's come back to it.
Okay. So the benefit of going to spiking neural networks is that you potentially could represent your deep learning model in something that is more energy efficient. So it would be, you're able to do it instead of taking 100 watts or 1,000 watts or even more, we're able to do something at maybe a few milliwatts. That's the dream. That's the hope. And that would take advantage of these neuromorphic chips that can operate at those sort of scales. So the deep learning field uses these continuous value neurons partially because they're information rich, but partially because things like backpropagation work well and require having continuous valued neurons.
Right.
And spiking is not, strictly speaking, continuous valued. A Hodgkin-Huxley neuron would be, but that's incredibly complicated. An integrating fire neuron is not, where you hit a threshold and that threshold causes some discontinuity in the response.
Yeah, this beautiful backpropagation algorithm that's so useful is just people are still trying to figure out how it could work in brains and spiking networks. I know there's a lot of work being done for that. So,
yeah, and I think so. A lot of the field is focused on how do we make backpropagation compatible with spiking.
Yeah.
And there's been a number of good studies, a lot of them by theoretical neuroscientists who've been going in that direction. Let's make backpropagation useful for spiking systems. And we thought about that, but we decided to maybe go a different way. And this is where, we kind of said, okay, let's set aside the neuroscience details for a second, and let's come up with something that might be useful for computing fields. We want to target something that's brain-like in its final form, but not necessarily take the brain-like path to get there. So if the neural networks require continuous valued neurons in order to train them, but we want our end result to be discrete valued spiking neurons at the end, what we decided to do, and this was really my colleague William Severa who came into my office one day with this idea, and it just made a lot of sense, and we went and implemented it, is that let's take a neuron, treat it as a continuous valued neuron for most of the training. So, if we think about a sigmoid where you have something that starts off at 0, it gradually increases to 1 and then tapers off towards 1. And you have this, the width of that sigmoid is kind of your dynamic range over which your neuron can be trained. What we decided to do is we train it with kind of a standard initialized network and then gradually sharpen those activation functions. So by sharpen, I mean that the range by which it's 0 or 1 becomes closer and closer together. And this sort of range where it's a value between 0 and 1, which would be the area that the neuron can learn, just gets tighter and tighter. Eventually, that's just going to hit a discrete step function activation, which effectively is like a spike.
That's a spike, yeah.
Or perceptron would be the computer science term, but in a spiking sense, it's the same thing. And so we just gradually sharpen these networks. And that's why the name whetstone came about, because you use a whetstone to sharpen a knife, and we're using whetstone method to sharpen these neural networks.
Nice. Okay. Gotcha.
And, it was something that was, I think, an interesting idea. It was something that we thought could work, but there was really no theoretical reason why it should work. But it does work.
Yeah.
And one of the things that was really nice is that we've gone in and looked at lots of different configurations of networks, several different tasks. So not only image classification, but things like reinforcement learning as well. And it turns out that this process of gradually changing the activation functions to fit the requirements of the hardware, and in our case, that's requiring a spike, it works. And there's no reason that this can't be extended to other sorts of constraints that one might experience in a real world use of a neural network. If I want to just gradually train my neural network to fit any sort of requirement, I incorporate that requirement into my training process. So we've been excited by it because it actually seems like it might bring neuromorphic hardware technologies to actually be able to use deep learning algorithms, which everyone talks about, but no one's really been able to do yet.
Well, so it's the advantage. Okay, so the way it works is you take an untrained network and you start training it like your run-of-the-mill deep learning network on these continuous values. And through the training, you sharpen and then eventually end up with spikes, essentially. And then it's ready for the neuromorphic chips. But does it continue to learn after that? Or then you have a completely trained network that then you just run on the neuromorphics?
So it would be a completely trained network that you just can plop onto the neuromorphics.
I see.
At that stage. You can't really train it anymore unless you have one of these algorithms, like a backpropagation version that's able to handle discontinuous activation functions.
But if you had that, you would just train it from that from the beginning, I guess.
Probably.
Yeah.
And it turns out that for most applications, the sort of trained network is the sort of thing you'd want to accelerate. So you can spend a lot of time training, and the training is actually quite expensive.
Yeah.
But once you've trained it, and you want to stick it into things like a self-driving car, for instance, or a cell phone, pick one of these sort of embedded applications where power might be the requirement, but you're probably not going to want to adapt your model continuously. That in theory should be able to just put a neuromorphic chip on your cell phone, put Whetstone trained algorithm on that, and you'd be able to, do face recognition or something. And then eventually maybe you update your model the way we update maybe update your maps on Google Maps or something.
Oh, yeah.
So that would be the idea, but we're really training we're really developing a neuromorphic version of what's called the inference mode of the deep learning algorithm. So not the training process, but just the operation of the trained network.
I see. So is this ongoing work? I mean, are we going to start seeing these things cropping up here and there, or what?
Yeah, so we've we're moving towards, I guess, both in terms of where can Whetstone go? We're putting it on different neuromorphic platforms. We've implemented it on several of the European platforms, Spinnaker in particular, and hoping to get those kind of on the existing kind of suite of technologies that are out there today. And then from a more theory point of view, we're starting to ask some questions about how can we use Whetstone for maybe some of the more challenging networks, and then maybe get to some of the questions you were asking, which is, how can I maybe change a Whetstone trained network and have it learn? Is there a way to combine this with some of the ideas of the Neurogenesis deep learning, for instance? So there are some ideas of how we might be able to adapt these things, how we can extend Whetstone to be able to do some more, maybe more sparse networks. One thing that we don't do, which the brain certainly does, is use the time dimension of when a cell spikes as part of the encoding. Whetstone converts everything to 0 or 1, which has the benefit that your neural network runs at the same speed that it would have run in a continuous mode. But it has the downside in that we're not really using the fact of when the cell spikes as a carrier of information. Our brains carry information, presumably, as much of whether a cell spikes, but when the cell spikes. And that's less of a feature of Whetstone today. So we want to kind of get some of that neuroscience insight into the algorithm going forward.
So is it, just occurred to me, is it mostly used in feed-forward learning nets, or are there recurrent neural networks that it's also used with? You bringing up the time aspect made me wonder about this.
So we've mostly done it on feed-forward nets. We've done a little exploration on recurrent nets. And I think that's where we'd really want to have some more explicit representation of kind of spike time as part of that.
Gotcha.
In recurrent nets. So that's kind of where we see some of the opportunity going forward.
Oh, cool. Well, let's transition here. And, we've talked about these neuromorphic chips. I want to learn a little bit more about NICE, the Neuro Inspired Computing Elements workshop that you've been doing for 7 years now? Is that right?
It's coming on 7 years, maybe 8 years at this point.
Yeah.
I think we just had our 7th.
So just tell us what it is and kind of where you are now with the workshop versus how it began, what kind of attendance it was, what kind of people were attending versus what kind of people are there now, et cetera.
So NICE started as a Sandia-led workshop, and the goal was, bring people together who are interested in neural-inspired computing, but not be kind of only hardware people or only application people or only theoretical neuroscientists, but rather bring people kind of from across the landscape. We wanted something really interdisciplinary. And, we did it for entirely selfish reasons initially, which was,
awesome.
We were trying to build up mind share within the national lab community and Department of Energy, who runs the national labs, kind of say, hey, this is an area that we should be investing in and thinking about going forward. And what ended up happening was, we partnered with Karl-Heinz Meyer, who unfortunately passed away last year, but he was one of the heads of the Human Brain Project on the neuromorphic side. So he led the brain scales effort and helped bring, worked with Henry Markram and others to get the Human Brain Project off the ground. And he brought a lot of that enthusiasm out of the EU into the workshop. And we were able to get other members of government, NSF, DOE, other agencies coming here, as well as various academics and national lab partners. So it was really sort of interdisciplinary from a technical point of view, as well as from a, at the time, especially a programmatic point of view. So we had researchers, we had funding agencies. It was basically just kind of bring a bunch of people together and figure out where this field was. Is it ready for prime time yet? So it's evolved from that, in that I think we've become more of a conference as opposed to a workshop. And I think we're probably going to change the name in a year or so to actually be a conference, because what's happening is that we'd bring people in, and originally it was invite only, and eventually people started saying, well, I'd like to come. Can I come present on this work? Or I have this grad student who's interested in learning about this. Can I bring this person along as well?
Yeah.
Then people start saying, I'd like to be able to publish papers at this workshop, and we weren't set up for that.
Like abstracts and stuff.
So sending in abstracts, but in the computer science field and in the electrical engineering field,
yeah,
people publish at conferences.
That's right.
By and large.
Right. Yeah.
And of course, that's not what I do or hadn't done. So it wasn't that we had thought about that from the start, but it was the community really started nucleating around this workshop, and we've, I think a lot of people have come most years now. There's a kind of a good contingent of people that make it there every year. And we've been trying to open up and reach out to people who are more neuroscientists or maybe more in different application areas that might benefit from this, machine learning field, for instance. And we tend to do a pretty good job of, I think, having at least several invited speakers who really are not part of the neuromorphic community come in, inject some insights and knowledge that may have been kind of unfamiliar to people in the community. So I try to always get some neuroscientists, maybe on the computational neuroscience side, that can come in and say, the active thought in the neuroscience community is pointing in this direction. You all need to probably move away from thinking of everything in this way or whatever.
Yeah.
So, and that's been pretty good. I think we've had some good speakers over the years. Most of our talks are online. So if you look up nightsworkshop.org, there are links to a lot of videos of talks over the different workshops.
I was going to say that, and that one of the more entertaining and there are a bunch of good talks from individuals, but I really like the panel discussions where it's a bunch of the speakers sitting around, passing the microphone back and forth, kind of giving their thoughts on the day, but also taking questions from the crowd. So I really encourage people to, of course, I'll link to it in the show notes to go check out the videos, which is just a great resource. And yeah, it's interesting to see the different backgrounds coming together and interacting. So,
yeah, no, I appreciate it. The panel discussions at the end of the days is probably the most entertaining part, at least for me. Every once in a while, you have to rein people in; they get a little carried away. But we've had some really good ones over the years. There are certain attendees that are very vocal in their views of how things work and should work, and makes for some interesting conversations.
Just to highlight sort of the variety of people, there was, one, this is a very specific example, but a guy stood up to ask a question. I don't know who it was. And he said, my background is in neuroscience, but then I went into artificial intelligence, and then I went into neuromorphics. And then, so it's like, he encapsulated all of the people that are there in one person, sort of, and so it's a really it's a cool, I guess, soon to be conference that I will hope to go to. It's interesting. I almost this year went to the Telluride Neuromorphic Cognition workshop, which is held in Telluride, Colorado, and I've been in touch with a few of the people behind organizing that. And there must be some overlap between NICE and the Telluride conference.
Yeah, so there's a lot of common attendees.
Yeah.
So Telluride, which I've never been to, and I really would like to go in one of these years. It's up the mountains from us down here.
Yeah.
But my understanding of Telluride is that it's very focused on kind of a 2 or 3 week long, hands-on, building neuromorphic systems, learning how to write algorithms and design kind of neuroscience capabilities into hardware.
Yeah.
So it's a very interactive, I'd say almost training experience that, for people at say a graduate student or postdoc stage of their career can go in and really become fluent in a lot of these neuromorphic technologies. And so I've heard only amazing things about Telluride. A lot of the people who run Telluride have come to NICE over the years, and they present their work, often showing kind of, here's some demos that were made at Telluride by these teams. And so it's an overlapping community. The neuromorphic field as a whole is not very big. In terms of people who are actively working in this area, it's still pretty small. So it's kind of an opportunity, fun growth period for this field.
What's your take? I mean, so you've been doing this for years now. What is your take on the dynamic between people from the academic world and these sort of more industry folks, more hardline computing-focused folks? I mean, do they interact well? Do they get along? Is there often strife? And from which side does that strife come from?
Yeah, it's interesting. And in being in a national lab, we sit really on the fence between those.
And you are, especially given your background. So, yeah. Do you moderate fights? Do you,
Well, I like to think that I can talk to both crowds. I don't know if I'm good at moderating the fights, but the thing that is interesting, and I think this is something that neuroscientists don't necessarily appreciate until you get out into whether it's an industry world or a computer science world, is how much application and sort of performance matters.
Yeah.
Compared to what is kind of intrinsically interesting from a scientific point of view.
That's a good distinction.
Some people are obvious about when they say something is interesting because I care about applications, or it's interesting because I care about just how the brain works. Other people don't tell you. They just get hostile. So it's an interesting thing, and it's a dynamic that I would say that most neuroscientists probably need to think a little bit more about as they start reaching out into machine learning worlds or computer science worlds, industry, and so forth. Because, most of these people are very smart. If you're in industry and you're running a research lab doing a multi-million-dollar project on whatever, they're very smart. They're intellectually curious people, and they do care about how the brain works and why the brain works the way it does. But their bottom line, the reason they have a job, the reason they're at that meeting, is because they're trying to come up with a solution for a problem.
Yeah.
It's actually not that different than when I was at the Salk and working in Rusty's lab as a grad student, and we would talk to people from the Christopher Reeve Foundation, where, spinal cord injury researchers. And the people at the foundation, they were interested in curing a disease. And at the point where your research, when you're giving a talk and your research started to be about, well, it's really interesting how this gene interacts with this gene, or why this molecular pathway does this, and they're all of a sudden you see them tune out.
Yeah.
Because they're like, this is not curing this disease. This is not curing spinal cord injury. It's not curing depression. And the same thing happens in machine learning and neuromorphic computing. At some point, people have to make money off of this.
Yeah. Who the hell cares about serotonin, they'll say, for instance.
Yeah. I love serotonin, but it's hard to defend it sometimes.
Sure. Well, that just picked that out of a hat randomly, but yeah. Okay, again, that is the first part of my conversation with Brad Aimone. In the next episode, we'll pick up right where we left off and go on to talk about how what we're learning about brains could be the key to progress in computing beyond Moore's law, which is slowly dying. Plus all the usual tangents and such. All right, see you then. Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.